All right, we are going to be going over the energy that's involved in chemical reactions and be talking about heat of reaction. So a reaction can either be endothermic, which means it's going to overall absorb energy, or it can be exothermic, which means overall it's going to release energy from the reaction. So the energy of a chemical reaction, we usually measure in heat. We'll be talking about energy in terms of enthalpy. So anytime you see or hear enthalpy, think energy, and you'll see it represented with a capital H. So just to review, and you saw this in the gizmo a little bit, in reaction, bonds are both broken and formed. So if you think about that little acronym BARF here, just to review, breaking is going to absorb energy, so energy will be absorbed as bonds are being broken within the reactants, but then as we form those new products, we're going to be releasing energy. So energy will be released as bonds are formed to make the new products. So as a chemical reaction proceeds from reactants to products, there's going to be an overall energy change based on the amount and types of bonds being broken, but also the amounts and types being formed. So when we look at all of this together in a reaction, the overall change is called the heat of reaction, which you're going to constantly be seeing delta H. This is the change in energy, or you'll see it the change in enthalpy. So this is the difference of the energy between the products and reactants, and represents the overall heat energy that's being absorbed or released. So delta H is always going to be the energy of our products minus the energy of our reactants. And there's a lot of other delta H calculations that you would do at different levels of chemistry. We're just going to focus in on this idea of products minus reactants to figure out if we have an endothermic or exothermic reaction. So the two types, again, that we're going to talk about are endothermic and exothermic. Endothermic reactions involved an absorption of energy. So this is going to be a positive delta H. And that's because if you think about products minus reactants, if we're absorbing energy, the potential energy of the products at the end, because there's been an absorption of energy, is greater than the potential energy of the initial reactants. Okay, so that's where that positive comes in. It represents absorption of energy for a reaction overall, which then indicates an endothermic reaction. One little thing, you can see this on the diagram, which we're going to be getting into more complex energy diagrams. We have our initial reactants at a certain amount of energy, and then by the end of the reaction, the products have more energy. This represents a general absorption of energy, which is our endothermic reaction. This would be a positive delta H. One little thing is when we actually write in energy into our chemical equation, you're always going to see endothermic reactions with energy written on the reactant side. You'll either see it as energy, you could see it as heat, you could see it as a certain number, of kilojoules, all of those representing an endothermic reaction, as long as it's on the left-hand side. For exothermic reactions, this has a negative delta H. Now, whenever we talk about in terms of the value or delta H, you'll always see the negative sign, but you won't actually see the negative in the equation. I'll mention that again shortly. Oh, and then this is a little error here. When energy is released by reaction overall, this means then that if you think about the original equation, products minus reactants, if you're getting a negative, that must then mean that your final products, if you look at this diagram over on the right, have to be less than your initial reactants, so that you have a small number minus a larger number. So in this case, the potential energy of your reactants is going to be greater than the potential energy of your products. Okay, those reactants have like kind of extra energy when they react. They form the products and then release some of that energy. So the products no longer have it. So you can see that here you have your reactants at a higher energy on the right-hand side. Energy is going to be released to form the products that are at a lower energy. That gives you then a negative delta H and represents an exothermic reaction. The products are lower in energy because there's been energy released to form them. When we write in energy or express our delta H in our equation, energy is going to always go on the product side. And again, you can see that as energy or heat or a certain number of kilojoules. One big thing is you don't actually fill in the negative in the equation. The negative represents exothermic. The negative is showing you that it's going to be over on the product side to represent an exothermic reaction, but you don't actually write it in as minus there. So just be careful. You'll see some examples through the practice and so forth. Okay, so just some general things with our delta H's and our changes in enthalpy. The other part of this is using table I, which is a whole chart in your reference tables based on your heat of reactions. You'll see that you'll have various reactions here. You have your combustion reactions on the top part. Then you'll see all these synthesis reactions in the middle segment. And then you'll see various salts that dissolve. And I should stop right there with the exception of the formation of water at the very bottom. One little thing I like to point out is they actually on table I mention that the delta H values talk about the molar quantities represented in the equation, but also that the minus sign indicates an exothermic reaction. So it kind of helps you out with remembering which is exothermic versus endothermic. All right, so let's just go through a few examples here. Here we have our first equation, and it wants us to know what the delta H is. So the reaction, which really this should say delta H here. So table I, we're going to find that equation. This is a synthesis reaction. So that kind of helps me look in that middle segment. And then I'm going to find it right here in the middle. And that tells me what my delta H is. So my delta H for this reaction is negative 91.8 kilojoules. Okay, since this value is negative, I then know that this reaction is exothermic. So it's going to release energy. So when we go to actually fill in this value, it's exothermic. So I'm going to fill in the energy on the product side over on the right-hand side. So I'm going to fill in the 91.8 kilojoules. Okay, and again, the exothermic part is represented with it being shown on the product side. I don't actually show the minus with my energy in the equation. So this reaction produces 91.8 kilojoules of energy for every 2 moles of ammonia. So for every 1 mole of nitrogen and every 3 mole of hydrogen producing 2 moles of ammonia, it's going to produce this 91.8 kilojoules. So how much energy would be produced if only 1 mole of ammonia was produced? So if I cut the moles in half, I'm also going to do the same thing with the 91 kilojoules. So I would have 91.8 kilojoules divided by 2, because I need half of it, and that's going to give me 45.9 kilojoules. You could almost set up a proportion similar to how we did like mole to mole calculations earlier, but just as long as you can recognize either cutting it in half or doubling it or tripling it, you should be fine. So I just put that down in the note here. Whatever you do to the moles, your coefficients, which your moles are represented by your coefficients of reactants or products compared to the original equation, you also have to do the same thing with the amount of energy. So if I'm going from 2 to 1, I'm cutting the moles in half for my equation, so I'm going to cut my energy in half. If I were to double the moles of a product, then I would double the amount of energy produced. Okay. All right, getting into another example here, we have another synthesis reaction. For this one, I'm looking at my H2 plus I2 is yielding hydrogen iodide, and here I get a positive 53. So table I lists this reaction's delta H as positive 53.0 kilojoules. Okay, this H value is positive. So this represents an endothermic reaction. So in this case, if we're going to fill in the energy, because it's an endothermic reaction, I have to show that the reactants are going to absorb energy in order to become the products. So I have to fill in my energy on the left-hand side or on the reactant side to represent that. Now this reaction absorbs that amount of energy when 2 moles of hydrogen iodide are synthesized or formed. So how much energy would be absorbed if 2 moles of hydrogen iodide were decomposed? So what would the energy be if I had those 2 moles of hydrogen iodide decompose into hydrogen and iodine? Okay, I reverse the equation. So my delta H originally was positive 53.0. If I then reverse it and think about how I would then write this, this energy moves right with the hydrogen iodine. So instead of being on the reactant side with them, it is now on the product side. It's supposed to be a 3 there. So now I can see the reverse of this is now an exothermic reaction. So now my delta H is a negative 53.0 kilojoules. So if you reverse an equation from table I, you also then have to flip the sign for your delta H. Okay? All right, so see if you can apply this all in the practice and then try out the little check-in assessment and you will be all set.